So we very much look forward to your talk, Kitt, and thank you for coming.
Thank you very much, Hannele, for this wonderful introduction. I'm going to share my screen and see what happens here. Here we go. Let's see. It should be, you see it now?
Very good.
Okay, so I'm going to turn to more the mechanisms underlying the effects of caloric restriction in NAFLD and type 2 diabetes. And I want to start out with just sort of the general concept of what we see is the real issue, not as much as obesity, but really when fat builds up in the insulin responsive organs, such as the muscle and the liver, it causes specific insulin resistance in these organs. And there are several ways that we can do it. There are two sides of the equation. The most common is, of course, as we've been discussing, is excess caloric intake, so that we get an overload of lipid that builds up in the muscle and in the liver. And in humans, we actually see that it's the muscle first, and then eventually we get hepatic steatosis as well. There's also issues where we can, or situations where we can see that there are fat cell defects. And we have studied people with generalized lipodystrophy, where there basically are no fat cells, and therefore there is an overload of fat storage in the liver and in the muscle. But there are other fat cell defects as is being uncovered right now that leads to increased delivery of fat to these insulin responsive organs. The other side of the equation is, again, the oxidation of fat, because if we see reductions in oxidation of fat, that will lead to a backup of lipids in the muscle and in the liver. And we have seen that we can acquire that with aging, just healthy aging. Most healthy older people are insulin resistant, and we have seen that they have reductions in mitochondrial fat oxidation. It can also be inherited, as we have seen in our young 20-some-year-old insulin resistant offspring of parents with type 2 diabetes. And there, a mitochondrial defect inherited is most likely due to some kind of a reduction in mitochondrial number. But it also leads me to what I really want to talk to you about, and that is really what can we do to reduce lipid accumulation in these insulin responsive organs and then reverse insulin resistance, which is ultimately the goal of metabolism. And one thing is overweight and our ideal of how we should look. The other one that really matters to us is metabolic health. And could we, in certain instances, when we come back to treatment, increase fat oxidation in liver that would reverse insulin resistance? But let me start out with sort of what we started out thinking way back in the beginning of the 2000s. We said, we see that people with type 2 diabetes have hepatic steatosis and hepatic insulin resistance. If we're right that this fat buildup in the liver is the cause of this hepatic insulin resistance, then if we get rid of it, it should actually improve insulin sensitivity and maybe even reverse diabetes. So we recruited a group of people with type 2 diabetes. We also had a control group shown in the light blue here. And we took the anti-diabetic medication away from the type 2 diabetic patients and then put them on a caloric restriction diet of about 1,200 calories a day. We used a liquid diet at that time. It's a very simple diet for people to follow on a short-term basis. Of course, this is a research study. And when there are no other distractors, then this is what you eat, and it's easy. But it also is high intensity, of course. It is a one-to-one study when you have to monitor people like that. But anyway, as shown here, after about 16 weeks, up to 16 weeks or 4 months, we saw normalization in fasting blood sugar levels in the patients with type 2 diabetes after this caloric restriction intervention. What I want to point out is that before the weight loss shown here, or the caloric restriction shown here in yellow, the patients with type 2 diabetes were obese with a BMI of about 30. And after the weight reduction, which was about 8 kilograms or so, and that has become the convention now, you need to lose about 10% of your weight, which is probably right. But after the intervention, they were still overweight, if not obese. So they didn't get back to high school weight. But what happened then? We measured liver fat. We used proton NMR. And we find that people, just like anyone we see with type 2 diabetes, pretty much have hepatic steatosis, and they had about 12% liver fat before the dietary intervention. And the liver fat went all the way down to 2.2%, which is something I also want to come back to again, because the current cutoff for normal liver fat is about 5.56%, as Roy Taylor pointed out from the Dallas Heart Study. Trepaniak study there said 5.56 is normal. We got down to 2.2%. And yesterday there was a discussion of whether when you reverse hepatic steatosis, do you also normalize hepatic insulin sensitivity? And in some studies, they couldn't see it, as we discussed yesterday. We measured rates of glucose production. You can see here we saw a nice reduction after the caloric intervention, caloric restriction intervention. And we were able to, and we got liver fat down to about 2%, to see a complete normalization of the ability of insulin to suppress hepatic glucose production, i.e. reverse hepatic insulin resistance. So that leads me to how do we define what normal liver fat is? And that takes us to a study we just recently published, and we examined a group of some 2,300 healthy people that we have studied over the past 10 years or so. And we divided them up into Asian Indian, people of Indian descent, either born in the US or born in India, or non-Asian Indian. And the reason we did that is we have previously shown that people with Asian Indian descent have a higher prevalence of insulin resistance and hepatic steatosis than any other group. And in fact, we see hepatic steatosis in the young people, which we don't see in the non-Asian Indian populations. So from the non-Asian Indian group, we selected the group who had normal weight. That means their body mass index was less than 25, and that was about 1,500 people or so. And in this group, we, like in all of them, we had dietary questionnaires. We had physical activity measured, where we gave them pedometers to wear for 3 days. We measured blood pressure. We did glucose tolerance test and measured insulin, so we could calculate the insulin sensitivity index from glucose and insulin. And we also had the fasting HOMA-IR, which is fasting blood sugar and insulin levels. And here we measure liver and intramyocellular and extramyocellular lipid in the muscle, with proton MRS at 4 Tesla. And so we looked at the distribution of hepatic lipid content in these lean BMI less than 25 non-Asian Indian individuals. And someone was asking before how we measure the liver fat with proton NMR. You can see on the left side, that's a simple image that shows the coil is sitting over the abdomen, and then we place a voxel inside the liver, and we measure fat and we move the voxel to 3 different positions in the liver and get an average of these 3 positions. On the right side, you see the actual spectrum where we have a water signal and we have this signal from the lipid. And that allows us to directly calculate the fat in the liver fat content in people non-invasively. I will add a little comment to the Dixon method, which we also use in some of the people who are too heavy to go into the magnet. But we find that the Dixon method is actually less sensitive in the low range of liver fat than proton MRS. Anyway, so here's the distribution of fat in the liver in these 1,500 or so normal weight individuals. It's skewed a little bit, but the 95th percentile is 1.85. So that's what we would say would be the 95th% cutoff for normal liver fat in this group of people. The question then becomes, does it make any difference to redefine what normal liver fat is? Does it have any implications for metabolic health at all, or is it just sort of a finding? So we went back to the group of people, non-Asian Indians, all of them independent on their BMI, and then we had about 1,900 or so, and examined metabolic markers in this group. And what we did was we took the people who had, in this group, who had liver fat less than our cutoff of 1.85% and compared them to the people who had liver fat in between this cutoff and what we consider the normal cutoff at this current time. And as you can see here, all of the metabolic markers, the markers of the metabolic syndrome, triglyceride, cholesterol, LDL were elevated, HDL were lower, uric acid was elevated, insulin was elevated, HOMA-IR was elevated, and insulin sensitivity index was lower in this group. So it does make a difference. These people they are healthy, but they already have markers of the metabolic syndrome, given that the liver fat is over 1.85% or 2%. I want to just go over the concept of how we understand how hepatic insulin resistance develops. And these are studies both done from our experience in humans and also for rodent models of type 2 diabetes. So here we have the liver, increased lipolysis in type 2 diabetes. There's increased chylomicron remnants that are delivered to the liver that increases long-chain CoAs. Long-chain CoAs increases that leads to increases in diacylglycerol and triacylglycerol, that's triglyceride, as you know. Increases in DAGs, as we call it, lead to activation of PKC epsilon. And there will be a test at the end. This is the plasma membrane bound subfraction of DAGs that's called SN 1.2. That is the actual activator of PKC epsilon. And really for treatment, when you think about it, that's a very small pool of lipid that we just have to get rid of. We will see later on. Activation of PKC epsilon leads to a cascade of activation that leads to insulin resistance or decreased insulin sensitivity, so that in the postprandial state, you will actually see less glycogen synthesis in the liver. Long-chain CoAs go up, they increase acetyl-CoA in the liver, and they increase pyruvate carboxylase activity, leading to increased gluconeogenesis. So with decreased insulin sensitivity and increased gluconeogenesis, we see increased glucose production in type 2 diabetes. Now with caloric restriction, chylomicron remnant delivery to the liver is decreased. We see decreases in long-chain CoA. We see decreases in DAGs and TAGs, and mainly in the subfraction of DAGs that are plasma membrane SN 1.2. And with that, decreased activation of PKC epsilon and increased hepatic insulin sensitivity. The decrease in long-chain CoA leads to decreases in acetyl-CoA and a decrease in pyruvate carboxylase flux or activity, which is consistent with decreased gluconeogenesis. And we see decreased glycogenolysis delivering to glucose production, and thus overall a decrease in glucose production. So in summary of that, plasma membrane SN 1.2 DAG content is decreased with caloric restriction. PKC epsilon activation is decreased, and that leads to increased insulin-stimulated hepatic glycogen synthesis. Hepatic acetyl-CoA levels are reduced, and that leads to reduced pyruvate carboxylase activity and flux or gluconeogenesis. And then we see net hepatic glycogenolysis reduced as well. I want to then end up saying we actually have a method now where we can measure mitochondrial activity, and we can measure pyruvate carboxylase flux, and we can measure TCA cycle flux, which we call synthase flux, non-invasively in humans. And this is a method that we published a few years ago. It's called non-invasive assessment of hepatic mitochondrial metabolism by positional isotopic NMR tracer analysis, or in short, PINTA. And I will briefly describe to you what we're doing in that study, but it's basically a study that's done bedside. And what we do is a 3-hour infusion of 313C labeled lactate. And what we monitor is lactate, the carbon-13 from lactate being incorporated into plasma glucose. So at the end of the study, we just collect a blood sample and we analyze that for the glucose M1, M+2, and lactate M+1 with GC-MS spec. That will allow us to calculate the ratios of PC or pyruvate carboxylase flux to TCA cycle flux mainly, and ratios of VPC, pyruvate carboxylase flux, to glucose production. But we can deconvolute these ratios when we at the same time measure glucose production by giving D7 labeled glucose throughout the study. A large sample at the end is analyzed then by high-field NMR for glucose enrichment in each of the 6 carbon atoms in glucose, and we can then perform our calculations that I will show you. And what I want to just say in this last part of the study is this the study that we wanted to see what actually is the crosstalk between the liver and the muscle during starvation or caloric restriction. So we have seen in rodents that starvation decreases rates of hepatic oxidative metabolism, and that this seems to be associated or attributed to a reduction in glucose-alanine cycling. And we wanted to see if this happens in humans as well. Just want to quickly go through the glucose-alanine cycle with you. So the muscle is releasing alanine to the liver, transported to the liver. In the liver, alanine is converted to pyruvate and the amino group is going into urea. And the liver makes glucose from pyruvate via gluconeogenesis, and then the glucose is transferred again to the muscle, where by glycolysis it's converted to pyruvate. And alanine is then restored by alpha keto acid that adds the amino group to it. So that's the glucose-alanine cycle, and it's basically a crosstalk between the liver and the muscle. So we recruited a group of 15 healthy young men, and they underwent a 12 and afterwards a 60-hour prolonged fast. And let's just see here. So you can see here glucose production decreased by about 25% with the longer term fast. And I have a hard time seeing here. So we saw no differences in the pyruvate carboxylase flux with this intervention. But we saw the relative, that's one of the outreads of PINTA, we saw the relation between pyruvate carboxylase flux and mitochondrial oxidation was increased. And since pyruvate carboxylase flux didn't change, when we calculate the numbers, the net rate of citrate synthase, so which really is hepatic TCA cycle flux, decreased by about 50% during this prolonged fast. We measured in a subgroup that we measured alanine turnover just to get at the glucose-alanine cycle. And we found that with the 60-hour fast in this subgroup of people, that there was a 30% reduction in rates of alanine turnover, which reflect about 5 micromoles per kilogram per minute or so. And so just want to end up, we had to talk about redox state. And what we saw here was that we actually saw an increase in plasma beta-hydroxybutyrate to ACAC concentration. So reflecting that we get an increase in redox with this 60-hour caloric restriction in healthy people as well. Then we wanted to see, is this reduction in mitochondrial TCase, hepatic mitochondrial TCase flux really reduced to glucose, attributed to glucose, less glucose-alanine cycling in these people. And that led us to this not so fun idea, is to go back to the people and ask, would you like to repeat the 60-hour fast? But 9 of these 15 people did so. And we repeated the PINTA study after the 60 hours of fast. But during this PINTA study, we replaced alanine by that 5 micromoles per kg minute that we had seen was reduced by during the 60-hour fast, to see does that restore anything. And here you can see we saw a nice rate raised in glucose production, go back 30%. Pyruvate carboxylase went up a little bit. The ratio of pyruvate carboxylase to mitochondrial oxidation went down more, though, by 22%. And thus we saw a net increase in hepatic mitochondrial fat oxidation of about 68% just by replacing alanine. And with that replacement of alanine, we saw a nice reduction again in hepatic redox state. So it is something that we had a discussion about yesterday. What is hepatic redox? And it was something we thought about in those days. And we can see that it's reversible. And what we need to, of course, understand furthermore is what is really the effect. Is that the driving factor, or is it something else that I want to come back to? But with the 60-hour fast, we saw 25% reduction in rates of glucose production. We saw 50% reduction in rates of hepatic mitochondrial oxidation, no change in rates of hepatic carboxylate flux, and a 30% decrease in the rates of alanine turnover, which was restored after we normalized alanine turnover during the 60-hour fast. So these studies demonstrate key role for glucose-alanine cycling in the regulation of hepatic mitochondrial oxidation during starvation in humans. So basically, there is this crosstalk between the liver and the muscle during starvation. And we need to find out whether it's the actual reduction in blood sugar or it really is the redox state that is the actual messenger between the muscle and the liver during starvation, because how does the muscle know? So with that, I just want to thank you for your attention, and I want to thank all my collaborators and the funders over time, and I'll take any questions, please.
Well, thank you, Kitt, for this very nice presentation, and congratulations for very elegant studies. Maybe I'll start off by, I mean, is this starvation, which somehow it's the doctor's dream that every patient we have should do starvation so that they could get rid of liver fat and all the metabolic problems. But you show that mitochondrial oxidation actually goes down 50%. So should they keep eating protein or what? Because isn't this theoretically harmful, this decrease in oxidation? What is it, good or bad?
So this is just really just an idea to get into talk about. I would never say people should do starvation at all, and I totally believe that, again, what we want to get at is we want to see here, how is it during starvation that the liver and the muscle are talking to each other? What is it? Is it the substrate delivery that reduces mitochondrial fat oxidation? And the situation of starvation, so this is a mechanistic study, is not what we're talking about in caloric restriction. So what we are talking about in this session, and that's the most important part, is to get rid of the liver fat and muscle fat, the excess ectopic lipid accumulation. And there are many ways to get there. It certainly shouldn't be starvation, but it should be caloric restriction. However, as we and the previous speakers have pointed out, that's very complicated, and we can mobilize big groups of psychiatrists, psychologists, and exercise physiologists. It's all good for health. But what we really want to is just to get rid of these small pools of fat in the ectopic sites, and that's really the DAX. And so what we're aiming at is to see overall, can we find a way to safely do this? Because diets are very, very hard to keep for people, as we've been discussing. Or is it such that we can actually just increase, instead of decrease, increase hepatic fat oxidation, and thereby, independent on weight loss, reduce these lipid pools that are deleterious to our health, independent on our sort of ethical or vanity idea of what should we look like. There is certainly ideas with, I don't agree with obesity, severe obesity, and lack of exercise is not good for us, but we can cure this condition, and we see it in many of our groups of people who are not, like Roy Taylor pointed out, are not obese and really shouldn't be losing weight in a sense, but can we just get rid of this and restore metabolic health?
Thank you. Our panel is now very awake. We have 3 questions, but before that, let's go to the audience questions. So Birgit Andersen, first is a comment, great talk. And second one is, I wanted to ask if the alanine infusion increased plasma glucagon, and if it did, why did beta oxidation decrease?
So we didn't see any differences in, we did see a slight increase in glucagon, that is true. And I can't remember exactly how much it was, but we didn't see any significant increases in glucagon. So we don't think that's the actor, and we didn't see any changes in thyroid hormone either. So we don't think that was the responsible hormone.
Okay, and second question from Dr. Marchesini. Severe calorie restriction promotes clearance of fat in the liver with minimum weight loss. Does it mean that liver fat is a rapidly exchangeable pool of scarce significance in total body pool? In principle, it might be possible to clear liver fat by intermittent fasting, independent of weight loss.
I totally agree that that's Julio is right to the point there that it is a very small pool of fat to get rid of, and that was the first thing we saw when we did this sort of short-term caloric restriction in our patients with type 2 diabetes. They were also obese to overweight after the intervention, yet their liver had totally cleared out of fat and had normal insulin sensitivity. Their blood sugars were normal. So it is a very small pool of fat to get rid of. And you could say we can try intermittent fasting and we can try ketogenic diets. And like Roy says, whatever works for you. But I just, what I see, we've been studying people on a ketogenic diet, people who've been on it for 1 or 2 years or so. And the reality is, as I see it, they believe they're on a ketogenic diet, but you can't keep it. So they start to add a little bit of carbohydrate to it. And we will be publishing this, but that was really deleterious to their health, because in face of a high caloric intake and just a little bit of extra carbohydrate, they get rampant hepatic steatosis. So we shouldn't fool ourselves with these things, because these diets are very, very hard to stick with for life.
Okay, thank you. Then Amalia was the first one of the panel.
Kitt, very, very interesting. Congratulations for this data. So I really like your data on the crosstalk between the liver and the muscle. But I was thinking, during prolonged starvation, we know that there is an increase in gluconeogenesis that I believe is probably mainly from glycerol, because as you saw that there was less from alanine. So do you think that could be also a mechanism saying to the muscle, do not increase proteolysis, because otherwise with prolonged fasting, it will decrease the muscle size, and so will be deleterious. So it's sort of also a signaling saying this, because if I remember your data, when you infuse alanine, you also have a little increase in glucose production. So probably you have also an increase in gluconeogenesis due to the increased glucogenic substrate.
So that's such a cool question, because you're hitting right on it. But there is a significant difference between what we did here was, I think actually we went up to 72 hours of starvation or long-term starvation in people. And that's when you run into proteolysis. And we're actually addressing these questions now with a fellow that we have from Denmark, Katrine Galsgaard, who's addressing these effects on proteolysis for long-term starvation and other issues. But that's not really what this study was all about.
No, I thought that, I know that was not about, but I thought, since you have less alanine, probably there is something saying to the muscle, do not increase proteolysis, because also your insulin is not high usually during starvation, because you have a decrease in glucose. So there is no stop in proteolysis, but still you have a decrease in alanine. So that means the alanine during starvation is coming from the muscle, it's not coming from other sources. So it should be something like that. Did you also measure other amino acids just to say if they were changed or not?
I do not recall whether we did or not, actually, I'm sorry.
Okay, I think we have still many questions. So Professor Taylor.
Thank you, Kitt. Lovely data, as always. First of all, it's very exciting to see your data on non-Asian Indians, because here we have an ethnic group with a tendency to increase liver fat, and you demonstrate very nicely that it's not necessarily so. Now, that's important because there's been a lot of talk of type 2 diabetes being different in different ethnicities, which is bizarre when we consider the effect of intervention being so uniform. And indeed, calorie restriction studies in Indians, admittedly not living in the US, showed just the same effects. So even though the threshold might differ, the metabolic effect of taking away the liver fat is the same. But I'd like to just comment on your normal value. That's fantastic to see you defining this 1.8 in the retune with our study of BMI under 27 in white European ethnicity people. Our mean was 1.4 for the liver fat. So I think it's so important to emphasize this with relevance not only to diabetes, but also with relevance to the predilection to coronary heart disease, for instance, and others. So I just wonder if you're able to comment more widely about the efficacy of this across different ethnicities.
Yeah, so I would like to comment on the Asian Indians, as you said, because we just see that this is a group of people who are sort of left shifted. So that at a lower BMI, they
Warte mal,
basically look
Schatz.
like
Ja, ich
anyone.
mache jetzt mal Schluss hier mit dieser NAFLD-Konferenz und brauche dann noch 50 Minuten.
Detlef, please. Okay, thank you.
Okay.
I muted.
We see that they're shifted such that at a lower BMI, but we showed in our PNAS study some years ago, about 8 years ago or something, that Asian Indians, you know, at a BMI of about 23 already look like a Caucasian who has a BMI of 33 with hepatic steatosis and well on their way to cardiovascular disease and all of that. And we did do dietary interventions. We had a weight reduction in them and moved their body mass index from about 23, 24 down to 21, and everything normalized. So they look just like anyone else. It's just that it happens at a lower BMI. And whether it is a sort of like dystrophy, it's something where we talk about, can you not store the fat in the fat cells or what, remains to be elucidated. And we're certainly also looking for the genes to see it. But yeah, to me, it's the same. Yeah.
Thank you.
Thank you. Shira, did you have your hand up or you had the same question as Amalia? Because I saw your hand disappear.
Thank you. Yes, I actually had the same question as Marchesini about intermittent fasting, how to take this data to intermittent fasting. Thank you.
Okay, thank you. And then we have, well, the last question is really what you perhaps already addressed. Are you optimistic that the lower cutoff value for liver fat content will be implemented in the near future for preventing detrimental metabolic effects?
That is certainly my hope, because as we clearly show that people with about over 2% liver fat or so clearly have or well on the way to develop the metabolic syndrome. And what we really are concerned about, as well as liver, you know, is also cardiovascular disease, really, which really is what it's all leading to. And we're working right now to figure out, because of course that's the big issue for the hepatologists. You know, they what are we going to do with all these people if we set the cutoff that low? So we're working right now to see, we have all these metabolic markers, and can we calculate some kind of an index where we can just see whether, you know, based on like a lipid insulin index or something that we're working on right now, to see that you can do simply out in the clinic, take a blood sample and say, hey, that's it, you need to we have some kind of an intervention, and hopefully we will be able to soon actually give people some kind of a drug or a pill that can help them reduce the liver fat.